Okay, so you've already studied the aberration of light, and we got that by basically trying to Lorentz transform velocities, right? And then we use those to calculate angles. Now we can keep doing those things. We can now find a Lorentz transformation for acceleration, and do the whole thing separately for each quantity. But a lot of things are simplified if we basically identify what are called four vectors. Okay, so again, some of this I think you're already familiar with, and for people who are not familiar with it, a four vector is any vector of four quantities that transforms according to the formula we have for the Lorentz transformations, right? So if you have the zeroth element of a vector, it transforms as if you're transforming time, right? And if the first element of vector is the direction in which you have the boost, and so it transforms according to this equation. And the second and the third element of the vectors, there's no boost along those, so they remain the same when you go from one frame to the other. So you already immediately know that the first four vector which you're familiar with is basically just the four position, right? And so we can get four velocity and so on and so on. Now, again, we said that the interval is invariant under transformation. So the same thing applies to the four vectors. So if your four vector is Ct, x, y, z, then the interval we have there, which is a naught square minus a1 square plus a2 square plus a3 square, that's going to be invariant, right? That is just the kind of distance we had, the ds square, in the first video. Now it also turns out, and I'm not going to prove it for the sake of time, is you can take four vectors and you can take their inner product, right? So inner product is just like a vector dot product. But again, when you're dealing with four vectors, you need to make sure that the signs come out right. So in a vector dot product, you just add all the three components after multiplying them component wise. But in case of a four vector, there is a flip in sign. And the same applies to to kind of a dot product between two four vectors a and b. So their dot product is going to be a naught b naught minus of a1 b1 plus a2 b2 plus a3 b3. Now it turns out that the inner product also is sorry, it's not zero. It's invariant under any Lorentz transformation. Okay, so that's an error. Sorry, strike out the zero there. And again, the uh, the quantity over here is just the inner product of a vector by itself. So the general thing to remember is if you take any four vectors and you take their dot product, including a vector with itself, you get something which is called a Lorentz scalar, in the sense that you can go to any frame and it should have the same value. Okay, so the first four vector, which you already know, is the four position, which is c times time and xyz. We've been working with that so far. Now let's make you can make new four vectors using four vectors which you already know. And the first four vector we are going to make is called the four velocity. So it's nothing but the derivative with time of your four position vector, and it gives you a four velocity vector. Now, a point to note here is when you take the derivative, you must take the derivative with respect to proper time, and proper time is basically a time measured by a clock that is instantaneously at rest with respect to a particle, right? So if you want to measure the four velocity of a particle, then you need to imagine that the particle is at rest in some frame, right? Let's say k prime frame. And then the tau here is the time measured in that frame. Okay, so it is a frame in which the particle is instantaneously at rest. Now, when you are observing the particle from the lab frame, let's say the k frame, then the time you measure is generally called the coordinate time, right? So you'll be, because it's called coordinate time because when I say coordinates, it's the coordinates which you are working with in the lab frame, right? And so that quantity t is called coordinate time. Okay, so coordinate time is dt. Now you already know from time dilation that the coordinate time is going to be gamma times the proper time, right? That's just the equation for time dilation. Now, okay, so what happens to the four velocity? You have a derivative with respect to proper time, and that there's just the Jacobian factor gamma, to go from proper time to coordinate time. And then you just have to take the derivative with respect to your coordinate time. Now, so if you take the zeroth component, so the zeroth component is c times t, and you're taking a derivative of c times t with your proper time. So that just becomes gamma times the derivative of c times t with dt, which is just gamma c, okay? So the first component is again the derivative with x, right? And so, the gamma, the Jacobian comes out and you get a derivative with your coordinate time. And that is just the velocity you measure of the particle in your frame. That is v of x, right? And so the 4 velocity just becomes c times gamma, the time-like element. And the other elements are just gamma times the velocity of the particle you are measuring. So the Cartesian velocity you measure in your frame. Okay, so that's just that's just for velocity. Now for momentum is just the 4 velocity times the rest mass. Now again, the rest mass is a scalar. It's a Lorentz scalar. The rest mass of a particle is a property of the particle. It doesn't depend on which frame you're in. So again, you can always multiply a 4 vector with a scalar. You'll get back another 4 vector, right? So this is the 4 momentum. And this quantity here, gamma m naught times v, where v is the Cartesian velocity, I sometimes call the relativistic momentum, right? And so gamma times m naught is called the relativistic mass. So this quantity is called the relativistic momentum. Now you can actually go ahead and show that this quantity here, the time-like quantity of a 4 momentum, is just energy divided by c. And so in relativistic mechanics that's the equation for energy. So E square, and this is the contribution of the rest mass energy of the particle, and that's the the kinetic contribution to the energy. Yeah, so you can just plug in the relativistic momentum. So instead of p square, you have gamma square m naught square c square. There's another c square, so it becomes c to the power 4. You can plug all these quantities in, and in the end you'll show that energy is gamma times m times c square. I mean, this is a result you already know. That the energy of a relativistic particle is gamma times the rest mass times c square. So gamma times m is the effective mass. And so what you have here is just energy divided by c, right? So the 4 momentum is energy divided by c as the time-like quantity, and the 3 space-like quantities are just the relativistic momentum. Yeah, so it's just an example of how you can keep making 4 vectors. And the nice thing about making 4 vectors is how they transform, right? You can just blindly apply the Lorentz transformation law to go from one frame to the other. So that's just the advantage of having 4 vectors, is you don't really have to think much about how to transform them. Once you know for sure it's a 4 vector, you can just blindly apply the Lorentz transform. Okay, so here's the fun thing which you can do. We just said now that the energy is like a 0th component of a 4 vector. And you know how the 0th component transforms, right? The 0th component just transforms like time transforms, similar to time dilation. So if you go from, let's say, the primed frame to unprimed frame, energy is going to just transform like time, right? Because it's the 0th component of a 4 vector, it should transform just like time transforms. So this is, if you may, energy dilation, just like time dilation. That's how time transforms. Now you can know how power transforms, right? Power is energy per unit time. So dE and dt transform exactly in the same way, which means that power is Lorentz invariant. Okay, energy is not Lorentz invariant, but power is. So don't get confused by the conservation of energy, right? Conservation of energy is a physical law. It just means that in any frame you want to work, energy is conserved. But if you want to go from one frame to the other, then the energy is not going to be the same, right? In a different frame, a different amount of energy is going to get conserved. Okay, so don't get confused between transformation of energy and the conservation of energy. The conservation of energy applies in any frame, but that energy itself is not the same. In like different observers don't agree about what total energy is. But the nice thing is power is conserved. Okay, so that's a very nice thing which we are going to be using, that the power is always conserved in any inertial frame. Okay, so let's go one step further. Now we're going to do 4 acceleration, right? So we have the 4 velocity. We again, take the differential with respect to proper time. That becomes gamma times the differential with respect to coordinate time. and then we are going to basically, this is the 4 velocity vector, right? So we're going to take the derivative of the 4 velocity. Now, if you take the time-like component, c comes out of the derivative, and derivative of gamma is just gamma dot, okay? So that's the time-like component, the first component of the 4 acceleration. Now, the second component of the 4 acceleration is, again, gamma stays outside, derivative with time of a product of gamma and Vx. Now, you can just use the chain rule there. So gamma times the derivative of Vx is just the acceleration, a of x, plus V of x times the rate of change of gamma, so gamma dot. So notice that the rate of change of gamma is not 0 because the particle is accelerating. So, you know, we are talking about a 4 acceleration. Yeah, so the other quantities are basically the same. Instead of x, you have y and z. Now, so you end up with the 4 acceleration, which looks like this. Now, a special frame, again, which we'll keep going to, is the frame in which the particle is instantaneously at rest. So which means that in that frame, gamma is 1 because the particle is not, you know, is basically non-relativistic in that frame. Actually, its velocity is 0 in that frame. And gamma dot is 0 because the particle is now instantaneously at rest. So notice that this frame definition keeps changing for an accelerating particle, right? For an accelerating particle, every time, at every tiny instant of time, you need to redefine the frame in which the particle is instantaneously at rest because its velocity is changing. But anyway, if you had that definition, then you get a 4 acceleration, which is extremely simple. You know, just place all gammas to 1 and put all gamma dots to 0. And you're going to get a 4 acceleration, which is just 0 times just the Cartesian acceleration in that frame. Okay, this is not in the lab frame; it is in the frame of that particle. Yeah, so you put just gamma dot of 0 and gamma equal to 1, you get this. Okay, so once we have acceleration, we can actually go back to some of the ideas we worked with, which is the power radiated by an accelerating charge. So in the previous week, we just showed that at least for a non-relativistic charge, we showed that the power radiated is dE by dt is 2q squared by 3c cubed times the square of the acceleration, right? So this is something which we showed, which was true only for, which was not a relativistically correct expression, right? This was assuming that things were not relativistic. Now, a common trick which you can use to go from a relativistically not correct expression to a relativistically correct expression is to again use this concept which you have of Lorentz scalars and, you know, how different things transform from one frame to the other, right? So you know that power is Lorentz invariant. dE by dt is Lorentz invariant. It doesn't matter which frame you're in. This value must be the same, okay? 2q squared by 3c cubed, these are constants of nature. So these are also Lorentz invariant. Now, on the left-hand side, you have a Lorentz invariant quantity, which means on the right-hand side, you should also have a Lorentz invariant quantity, which means that this a square here, if we can somehow write it in a form such that it doesn't violate the non-relativistic limit, but in a general way is Lorentz invariant, then we are done. Then we actually get the correct expression, right? So the easiest way actually the only way you're going to cast this as a Lorentz scalar is to take the 4 vector A and dot it with itself, right? We just said that at the dot product of 4 vectors is a Lorentz scalar. So if I just write the A square as 4 vector A dot 4 vector A, then I'm done. In the non-relativistic limit, this is just going to reduce to A square, but it is relativistically correct, right? The expression is relativistically correct because, you know, both sides are Lorentz scalars. So this is just, I mean, you can again go through the whole derivation and all the pain and or the painful algebra, but in many cases which you will encounter, yeah, it turns out that you can take a relativistically not correct expression, but just use your general understanding of intuition of Lorentz transformations and kind of cast it in a way that it is, you know, relativistically correct, and, you know, you end up getting the proper equations. Now let's see how this works out. Let's write this factor out in a lab frame, let's say, where we can actually do measurements, right? So I'm going to assume that there are 2 frames here. K is the lab frame where we are. K prime is the frame. I'm going to choose K prime as the frame where the particle is instantaneously at rest, right? So in this frame, its 4 acceleration, A prime, is just going to be 0. That's the time-like quantity, and A prime, the Cartesian acceleration, right? That is, we just showed that that is the 4 acceleration in that special frame where the particle is instantaneously at rest. And now I just want an expression in the K frame, right? Because that is the lab frame in which I am in, the coordinate axis which I work with. And so the question becomes basically a question of, transforming this quantity and expressing it in terms of the unprimed quantities, right? So if I write out the Lorentz, if I write out the formula for the power radiated in K prime frame, I'm going to just have over here, I'm going to have A prime. So I'm just going to have inner product of A prime with itself. And I just want to express these primed quantities, transform them into the unprimed quantities, and then I have the formula which I want. Now, you know how to do that already, right? Because you know how to do Lorentz transformations of 4 vectors. So let's just do it. Now, in the K prime frame, the power radiated is just the square of the parallel acceleration and perpendicular acceleration, right? And by parallel, I mean acceleration parallel to the velocity of the particle, and perpendicular, I mean acceleration perpendicular to the velocity of the particle, okay? Now, the trick is to go from A parallel prime to A parallel and A perpendicular prime to A perpendicular, right? And then we are done. Then we have an expression for the power radiated by an accelerating charge in the lab frame, which is what we're looking for. Okay, so we just write out everything as a 4 acceleration, right? And then we do the Lorentz transform and we are done. So the 4 acceleration in the lab frame is this, this is the general expression for the 4 acceleration, regardless of frame. And this is going to end up being the 4 acceleration of the particle in the lab frame if we choose gamma as the Lorentz factor of the particle in the lab frame and gamma dot as its time derivative, right? So that's basically the 4 acceleration of a particle. Now in the K prime frame, you have a scenario where the 4 acceleration is very simple, right? And so we have the K prime frame and the K prime, the lab frame and the particle frame. We have these 2 4 accelerations. Okay, this expression here is the same as here. I've just taken the gamma inside, that's it. Now we know how to transform between these 2 quantities, right? So let's say I want to go from K prime frame to K frame. I'm going to apply a Lorentz transformation, right? So let's do the Lorentz transformation for the perpendicular acceleration. So in this case, the quantity is perpendicular to the velocity, which means this term, the velocity vector here, that velocity term is going to be 0 in the perpendicular direction, right? So we are only talking about quantities perpendicular to the velocity here. So you basically, on one hand, you just get A perpendicular prime, okay? And on the other side, you basically just have gamma square times A perpendicular, right? So you have gamma square times A perpendicular, and this quantity goes to 0. If you only look at an axis which is perpendicular to velocity, there's no contribution from this quantity. You just get gamma square times A. So gamma square times A perpendicular is A perpendicular prime, right? That is just the, again, this is just the Lorentz transformation of the second and third element of a 4 vector, right? You just equate the 2. Right, there is the transform is basically you take one and equate it with the other, and anything which is perpendicular to the relative velocity is going to transform as a second or third element of a 4 vector, right? Anything parallel is going to transform as the first element, and then you have the time like. So the time like element, the 0th and the first element have that more complicated Lorentz transform. The second and the third just have a very simple. You just equate the 2. There's no transforming function, and so that's what I've done. I've just taken the second or third element of this, and I've just equated it with the second or third element of this. It just happens that because you have a v vector here, the second and third element doesn't receive any contribution from this term, so you just get gamma square times A. Okay, so that's how perpendicular acceleration translates. Now parallel acceleration is a little more complicated. So I'm going to write out the parallel acceleration. Again, now you have to take all of these terms here. So you get gamma square times A parallel plus gamma dot times V. V is the velocity of the particle in your lab frame, right? It's the velocity between the k prime and the k frame, is equal to, again, the Lorentz transformation had a gamma, and then it had this expression where you take the, where there were two terms, a time-like and a space-like component. Of course, the time-like component is 0 in this case. So you had minus beta c times time-like component, but that is 0. So you're only left with the space-like component. So this is the first element. This is basically the first element of this 4 vector, right? The first space-like element. Yeah, and then you basically, write all of this out, and then you're done. So you can get rid of one gamma from this entire equation. So you get gamma times A parallel plus gamma dot times V equal to A parallel prime. Okay. And now, the rest of it is just algebra to figure out what gamma dot is. So you know that gamma is 1 minus beta squared to the power minus half. So you can just use the chain rule and differentiate that. So you basically end up with the gamma dot is gamma cube times A parallel by C. Okay, I mean, this is just basic algebra, so I'll let you do it. And to get here, you just write out what gamma is. Gamma is 1 minus beta squared to the power minus half, and then just take the derivative of that with respect to time. You end up with beta dot, which is beta dot is basically the acceleration divided by C. Okay, so you write the whole thing out. So you get gamma times A parallel plus beta gamma cube times A parallel is A parallel prime. Gamma times A taken out, you get 1 plus gamma square times beta square. Again, this simple algebra. If you write out beta in terms of gamma, you just get gamma square for this quantity. So you end up with gamma cube A parallel is A parallel prime. Now you put everything together, right? In the rest frame of the particle, in the frame where the particle is instantaneously at rest, this is the power radiated, right? And I know how to transform now A parallel prime to A parallel and A perpendicular prime to A perpendicular. You just do that, you get the final expression. That's the relativistically correct expression. Okay, so the way you want to interpret this is the power radiated by the particle when you want to have A perpendicular and A parallel in the lab frame. And gamma is the Lorentz factor of the particle. Now, if you want to work in the instantaneous rest frame of the particle, then that's just the expression, right? You just work in the primed quantities. We just applied the Lorentz transformations to go from k prime to k frame, where the speed at which k prime frame was going with respect to your lab frame k was v, and the corresponding Lorentz factor was gamma, which is the velocity and Lorentz factor of the particle. And that is the relativistically correct expression for the power radiated by an accelerating charge. Now, you'll see that you also have some relativistic corrections for the angular pattern of radiation, which I'm going to do in the next video.